Then let us take the case of disk or the ring. Take this ring which is uniform. Calculate the moment of inertia about the axis which passes through the center of the ring, and that axis must be perpendicular to the plane of the ring. If you take this is x-axis, this is y-axis, this must be the z-axis. The moment of inertia about the z-axis passing through the center of the ring can be given by r square dm integral. R is the length of each segment from the axis, and that is none other than the radius of the ring. The small r is equal to radius of the ring, that is capital R dm. Take r square out of the integral because it is a constant quantity for all the points of the ring from 0 to mass of the ring. So, mr square is the moment of inertia of the ring about the central axis passing through its center. Now, let us take the case of a disk. We are discussing the calculation of moment of inertia for uniform objects. The disk of mass m and radius r. This is the z-axis. Find the moment of inertia of the disk about the z-axis. As you know, a disk is the combination of so many concentric rings whose radius ranges from 0 to the radius of the ring. Let us take the ring of radius small r and its thickness let be dr. And the area of the ring can be given by dA is the area of the ring. That is equal to length of the ring, that is 2 pi r, into the thickness of the ring, that is dr. That will be equal to 2 pi r dr. Mass of the ring is equal to total mass of the disk upon total area of the disk, that is pi r square, into area of the ring. That will give us m by pi r square into 2 pi r dr. Pi getting cancelled. So, you are getting 2m r dr by the square of the radius of the ring. This is the mass of the ring. The moment of inertia of the ring, recently we have calculated as mass of the ring into the square of the radius of the ring. Here the radius of the ring is r and mass of the ring is equal to 2m by r square into r dr. This is the moment of inertia of the ring. Needless to mention, always it is about the z axis. Since a disk is the combination of so many concentric rings whose radius ranges from 0 to the radius of the disk, we can write the moment of inertia of the disk is equal to sum of or integration of the moment of inertia of all rings. And substitute here the moment of inertia of the ring, that will be 2m by r square r dr into r square. This term is a constant. Take it out of the integral to get r square into r, that is r cube dr. And this radius of the ring ranges from 0 to r. So we are getting 2m by r square. After evaluation of the integral, we are getting r4 by 4, because the integration of r cube is equal to r4 by 4. From 0 to r, you are getting r4 by 4. Ultimately, you are getting the moment of inertia of the disk is equal to mr square upon 2. Sometimes we can get an annular ring, annular disk, better to say, or a ring of thickness, suppose T. Let us take the case of an annular disk of outer radius B and inner radius A. This is the stuff. This is the stuff. How to find the moment of inertia of the disk about z axis passing through the center? For this, let us take a ring, very thin ring of radius r and thickness dr. Let us take a thin ring of radius r and thickness dr. The area of the ring is equal to 2 pi r dr. And mass of the ring can be written as area of the ring into surface mass density, that is total mass of the disk, by total area of the stuff of the disk, that is pi v square minus a square. Substitute the area of the ring is 2 pi r dr into m by pi v square minus a square. Pi will be getting cancelled. So 2 m by v square minus a square r dr. This is the mass of the ring. The moment of inertia of the ring, as per the formula, we can write it as the product of mass of the ring and the square of its radius. Substitute the mass of the ring as 2m by b square minus a square into r dr. The radius of the ring is r. This gives us 2m by b square minus a square into r square dr. The disk is the combination of so many rings having the radius which ranges from not 0, from the inner radius of the disk to the outer radius of the disk, that is from A to B. Integration of the moment of inertia of the ring, that is 2m by b square minus a square into r square dr. That is a constant factor. Pull it out of the integral to get r square dr. R ranges from A to B. Therefore, this is 2m by b square minus a square r square dr. The integration of r square is r cube upon 3 from A to B will be equal to 2m by b square minus a square into b cube minus a cube by 3. So, that is 2m by 3. If we expand it, b square minus a square can be written as b plus a into b minus a, and b cube minus a cube can be written as b minus a into b square plus a square plus ab. This will be getting cancelled from both numerator and denominator. So, we are left behind with 2m into a square plus b square plus ab in numerator upon 3 a plus b in denominator. Well, we are getting this result, but at the end of the derivation, when you are getting the result, whether this is correct or not, we can check it in many ways. One of the ways dimensional. In the numerator, we are getting square of the distance into mass. In the denominator, we are getting the distance. So, if you take distance say we r square upon r, we are getting the mass into the distance as the answer, which is a wrong result because the moment of inertia is defined as mass times the square of the distance. Therefore, dimensionally this answer is not correct. It happens many times in the mode of calculation we may get wrong answer. Once you trace the answer is wrong, how to correct it? So, you have to check the steps you have done. Area of the thin ring, this is absolutely correct, this 2 pi r dr. 2 pi r is the length. If you just cut it and stretch, you are getting a thin strip of length L is equal to 2 pi r, and the thickness itself is dr. So, this is just like a rectangle of length 2 pi r and the breadth dr. Therefore, this area will be equal to 2 pi r length into breadth, that is dr. They are absolutely correct. Mass of the ring is equal to total mass by total area, area of the stuff, shaded portion. that is pi b square minus a square. M upon that area will give you the linear mass, surface mass density. It's not linear mass density because it is a plate-like structure or lamina into the area of the ring. After substituting this, you are getting 2r dr into m by v square minus a square. Absolutely correct. Next, moment of inertia. Moment of inertia of the ring is equal to its mass times the square of its radius. So, when you are putting the square, you have not put the square of the radius. So, here is the mistake. This step is absolutely correct, and here is the mistake. You have to put the square. When you put the square, this will be r into r square, this will be r cube. Here the mistake. How to point the mistake? That is an art. So, this will be r cube dr. So, integration of r cube is r4 by 4, not 3. So, 2m by v square minus s square, pull it out, and r4 by 4, you put the upper limit, that is b4, lower limit, that is a4 by 4. B square minus a square, this is in denominator. B4 minus a4 is in denominator, b square minus a square is in numerator. So, that is 2 will be getting cancelled. So, m b4 minus a4 can be written as a square plus b square into b square minus a square by 2 b square minus a square. So, you are cancelling this. Ultimately, you are getting the moment of inertia of this annular disk is equal to m a square plus b square by 2. This is the formula. It may be a disk, it may be a cylinder. About this z axis, this is the formula for the moment of inertia, valid for both disk and cylinder. And if a is equal to 0, its moment of inertia will be equal to zero plus b square by 2, m into v square by 2, and v if you put as a radius, so you are getting mr square by 2, which is none other than our general formula for the moment of inertia of the disk, complete disk without any circular hole about the z axis. This is a more general formula. All these derivations we are doing are based upon the concept, based upon the some limitation, or based upon the condition that the disk or the rod must be uniform. If the disk is not uniform, then how to solve the problem? Well, let us take the disk. Which is not uniform at all. Say the surface mass density varies linearly with respect to the radial distance. If this condition is satisfied, find the moment of inertia of the disk about the centroidal axis perpendicular to the plane of the disk. So, take the ring, following the general procedure of the derivation. For this thin ring of mass dm is equal to surface mass density, which is defined as dm mass of an element of the disk upon its area. Since this ring is extremely thin, we can also take dm as the mass of the thin ring and dA is the area of the thin ring. So, Iz is the moment of inertia of the disk about the z axis, is the moment of inertia of the disk is equal to sum of the moment of inertia of all the rings whose radius ranges from 0 to the radius of the disk, that is capital R. I ring is equal to m ring times the square of its radius as per the formula. Mass of the ring can be written as surface mass density into the area of the ring into R square. Area of the ring is equal to 2 pi r dr into R square. The surface mass density is not a uniform quantity or constant quantity, therefore you cannot pull it out of the integral. You have to substitute its value as a function of r into 2 pi r dr into R square. 2 pi and sigma naught are in product form, are the constant quantities. Take it out of the integral. You are getting r into r square into r square r to the power 4 integration of this, and the lower limit is 0, upper limit is r. So, evaluating the integral, you are getting R5 by 5. 2 pi sigma naught R5 by 5 is the answer. So, in this way, you can calculate the moment of inertia of a disk. It may be uniform, it may not be uniform. For uniform disk, that is m r square by 2. If it is not uniform, that is not m r square by 2. The answers will be different depending upon the way in which its surface mass density will vary. Let us take another example, that is, say, thin spherical shell. How to calculate the moment of inertia of a thin spherical shell? The thickness is very small. Compared to its radius. We have to calculate its moment of inertia about an axis passing through its center of mass or about any diameter. Let it be y axis. This is the thin spherical shell. The thin spherical shell is a combination of so many concentric, or better to say coaxial thin rings whose radius ranges from r is equal to 0, small r is equal to 0 to at this pole, to small r is equal to, or radius of the ring is equal to radius of the disk at this equator. If you take this ring, this is the thin ring. Its moment of inertia about the y-axis is I ring is equal to mass of the ring into square of its radius, that it be small r. Mass of the ring can be written as surface mass density at any point into the area of the ring into r square. The area of the thin ring, you cut it and stretch, you will be getting a thin strip of length 2 pi r and breadth not equal to dr, but it is this length, this particular breadth, this is the breadth. And this breadth can be calculated by taking some angular position, let it be theta. And this angle is let d theta. The breadth of the ring subtends an angle d theta at the center of the thin spherical shell. Therefore, the breadth of the ring is equal to r d theta, but not dr. So, the area of the ring will be equal to its length into its breadth, that is r d theta, and substitute the area here, that is equal to 2 pi r into r d theta into r square, where the radius of the ring can be given as r, because this length is r, and this projection of the radius of the sphere onto this x-axis, that is r cos theta. So, radius of the ring is equal to radius of the disk into the cos theta. Then this can be simplified as 2 pi sigma into r, this is small r square, into r, that is r cube d theta. Substitute the value of small r, 2 pi sigma r, that is r cos theta cube d theta. This will be equal to 2 pi sigma r cube into r, that is r to the power 4 cos cube theta d theta. Then the moment of inertia of the sphere can be calculated by summing of the moment of inertia of all rings. Substitute the moment of inertia of the ring as 2 pi sigma r4, take it out of the integral, this will be cos cube theta d theta. Theta ranges from 0 to pi by 2. And that will give you the moment of inertia of the upper half. For the lower half, this will be minus pi by 2 to 0. Therefore, same derivation, same expression will give you the moment of inertia of the entire sphere. If you take the lower limit minus pi by 2 and upper limit of theta is plus pi by 2, because from theta below is minus, above is plus. It's minus pi by 2 to plus pi by 2. Then it will cover both the halves, lower half and the upper half. And you have to evaluate this integral. After evaluating this integral, that is your home task. By using the ideas of mathematics, and then putting the surface mass density, since it is uniform, it can be written as total mass by total surface area, that is pi r square into 4, that is 4 pi r square. We have two by 3 m r square. This is for the spherical shell, thin spherical shell. Well, let us take the next example of solid sphere. The moment of inertia of a solid sphere. That is uniform sphere, and we choose any diametrical axis or any centroidal axis. Let it be y axis, say. A solid sphere is the combination of innumerable concentric thin spherical shells whose radius ranges from r is equal to 0 to the radius of the sphere. This thin spherical shell, let have the thickness, that is dr. Then the volume of the thin spherical shell is given as dV is equal to 4 pi r square dr. Its area is 4 pi r square and thickness is dr. Or you can just write volume of the sphere of radius r is equal to 4 by 3 pi r cube, and dV will be equal to 4 pi r square dr. dV is the volume of the thin spherical shell. Once you calculate the volume of the spherical shell, its mass, the mass of the shell is given as dm or m shell is equal to the volume mass density into the volume of the shell. dV is equal to 4 pi r square dr. So, the volume mass density, since it is uniform, can be written as total mass by total volume. But for non-uniform object, you cannot write like that. If you write like that, it may mean average density. But if the density is uniform, average density is equal to density at all the points or for any point of the body. For uniform object only you can write the density of the material is equal to mass of the material upon the volume of the material or the stuff, volume of the stuff. Its mass, let it be m, and volume is 4 by 3 pi r cube. So, this will be equal to 3m by 4 pi r cube. That is the volume of the solid sphere. Substitute here. So, 3m by 4 pi r cube into 4 pi r square dr. 4 pi will be getting cancelled. So, 3m by r cube r square dr. This is the mass of the shell. The moment of inertia of the thin spherical shell, as per the formula recently we have derived, is given as 2 by 3 mass of the shell into the square of its radius. Substitute the mass of the shell here. This will be 3m by r cube r square dr into radius of the shell, let be r. So, this will 3 will be getting cancelled. 2m by r cube r square into r square is r to the power 4 dr. If you integrate the moment of inertia of all the shells, you are getting the moment of inertia of the solid sphere. That's equal to 2m by r cube r4 dr integral r ranges from 0 to the radius of the sphere. This will be 2m by r cube integration of this will be equal to r5 by 5. After evaluation, after putting the limits, so ultimately we are getting the moment of inertia of the solid sphere is equal to 2m r square by 5. This expression is valid for uniform. All the expressions we are deriving are based upon the assumption that the solids are uniform. Let us tabulate all the derivations we have till now. Let us tabulate all the formulae we have derived so far. For a point mass, the moment of inertia is mr square. For a uniform linear object or rod, the moment of inertia about the centroidal perpendicular axis is equal to ml square by 12, where L is the length, m is the mass of the rod. If this is any end point, this will be equal to ml square by 3. For any ring, the moment of inertia about the perpendicular axis passing through the center of mass is equal to mr square. M is the mass of the ring, R is the radius of the ring. This point mass, this is rod, this is ring. If this is a disk, of radius r, mass m, about the z axis, the moment of inertia will be equal to mr square by 2. If it is annular, this will be suppose R2, inner radius is R1, outer radius is R2. Then this will be equal to m R1 square plus R2 square by 2. This is the disk. For thin spherical shell, of radius r and mass m, the moment of inertia can be written as 2 by 3 mr square. And at last, for a solid sphere of mass m and radius r, moment of inertia about the centroidal axis is equal to 2 by 5 mr square. After this, you can also try to derive the expressions for the moment of inertia of a hollow cone, thin hollow cone about this y axis passing through its vertex. That can be given by the expressions m given by the expressions mr square by 2. I am giving this as your home task. You can do this by taking several rings and calculate the moment of inertia of a ring of radius small r let the height be h, this angle is constant, so you can get a function moment of inertia of the ring as the function of r, or as the function of r, or as the function of y also you can calculate, and you have to integrate the moment of inertia of the ring to get the moment of inertia of the cone. And of course you can calculate. Of course you can calculate the moment of inertia of a solid cone of mass n, and base radius is r, and you can prove that about the axis passing through the apex and the center of the base. The moment of inertia can be given as mr square into 3 by 10. That you can prove by taking a thin disk at a distance of y, either from the apex or from the base, and the thickness of the disk is dy. Let us assume that rho is the volume mass density uniform, therefore total mass by total volume, that is 1 by 3 pi r square h. H is the height of the cone. Taking this thin disk, its moment of inertia about the perpendicular axis can be calculated by using the formula we have derived in this section. That's equal to mass of the disk into square of the radius of the disk, mass of the disk into the square of its radius by 2. And mass of the disk can be written as the volume of the disk. This thin disk acts as a cylinder of height dy, and base area pi r square. This is the volume of the cylinder or volume of the disk into the density. And if you integrate the moment of inertia of the disk, you are getting the moment of inertia of the solid cone. And this r ranges from 0 to the radius of the base of the cone. In this way you can get this expression. You can also take it as your home task and try it. Sometimes they may give you the truncated cone and they may ask you to calculate the moment of inertia. Suppose this is r by 2 and this is r. In the original expression, you have to just change the limit. Instead of 0, you have to write r by 2, and here r by 2 to r. That will give you the answer. And here mass, suppose its mass be m, and the volume cannot be 1 by 3 pi r square h. The volume will be volume of this segment. So volume of the entire segment minus volume of this segment will be equal to volume of this segment. All small modifications you have to consider before you tackle any problems or modified problems on moment of inertia. And we have some theorems called parallel axis theorem and perpendicular axis theorem. In the next class, we will talk about this. And after knowing all these theorems regarding the calculation of the moment of inertia, we can tackle some more problems in general. Thanks all of you.